In the previous video, we talked about closed ends. Now we need to talk about open ends because the end of a tube can be open. Now, this actually means that we have a different boundary condition. We are still going to get standing waves, but because the boundary condition is different, our standing wave is going to be a little bit different. So what's helpful now is to actually think about pressure rather than displacement, at least initially. So if we have an open end, right, our little molecules here are now free to interact with the air outside the tube. And the pressure out here is atmospheric pressure. So what we're going to say is that our boundary condition is actually that our pressure must be equal to atmospheric pressure at the end. And what you can think through here is that if this pressure right at the end decreased a little, well, air would be free to flow in. If this pressure increased a little, air is free to flow out. So really, you always have an equilibrium right at the edge, right at the opening of the tube, between the pressure inside and the pressure outside. That isn't to mean that you have a uniform pressure in the entire tube, because then you wouldn't have a wave. So we have nodes for pressure at each end when the ends are open. Now remember that for displacement, we said that going between displacement and pressure, the node for one was the antinode for the other. So if you're right at the end, your displacement is actually at a maximum value. So we have a maximum value at each end. So pressure has its maximum value, its antinode in the center, which is then actually your antinode, is your node for displacement. So another way to think through displacement being maximum at the end is that, again, these particles are going to move in and out a lot. They're very free to do that. But I think pressure is actually the easiest way to really grasp that, since that's truly where our boundary condition is coming from. And then we're using that relationship between pressure and displacement to see what the displacement curve would look like. If we go to a higher mode, again, notice that we had one bump here. This was our m equals 1, so we had one antinode in pressure. Now we have two antinodes in pressure. But our boundary condition is maintained. We still have zero difference in pressure from the atmosphere at the ends. And so you can trace out what your pressure curve is, and then from going from nodes to antinodes, you trace out what your displacement curve would be. So hopefully that makes sense. Again, physically, the way to get the boundary condition here is to think about pressure, but then to actually plot what displacement is, you use that exchange of going between nodes and antinodes. You can think about that as a derivative, sine to cosine, however you find that easiest to think about. Okay, so that's an open end. And in this case in particular, we're looking at open ends on both sides. Now let's think then about mathematically what condition that gives us. So we have one type of tube that is closed on both ends. We have another type of tube that is open on both ends. And for simplicity, we'll say they both have length L. Notice that when you have a pressure wave here, it had that node in the middle. But in your open-open case, your displacement curve has the node in the middle. So going between closed and open end and open, it's kind of like your pressure and your displacement shapes have just switched. But notice that the wavelength is actually going to still be the same. So we have this condition on our wavelength that for whatever mode M you have, your wavelength is 2L over M. That's going to be true whether it is closed, or open. And again, your boundary conditions are either nodes for displacement on the end or nodes of pressure on the end. But again, we've said that wavelength is the same whether you're talking about placement or pressure or displacement. So again, we get actually the exact same spectrum in each case. And remember that wavelength is kind of the starting point here because we can spatially see why this is true, but then we can calculate frequency by knowing what the wave speed is. And we can talk about our higher mode frequencies just in terms of the mode number itself multiplied by our fundamental. So again, open versus closed, the position of the nodes in pressure are different, or the position of the nodes in displacement are different, but your wavelength of the wave itself will actually be the same. There's a third option, perhaps obviously, which is one end being open and one end being closed. And in this picture, the left one is shown closed, the right one is shown open, but you could imagine obviously those being flipped, and then the shapes here would be flipped as well, but your wavelength would stay the same. So this is actually something we're going to need to talk about a little bit more because it's a little more confusing. When we talked about closed versus open, we said that the wavelengths are the same, but now look at what's happening over here. I have, if I look at, for instance, displacement, a node here, but then I have an antinode there. I don't actually even come back to my node. But the same thing happens in pressure. In pressure, I have my antinode here, and I have my node over on that side. What's a little more clear is if we go up to a higher mode, you can see now that my wavelength in this one corresponds to this if I'm looking at pressure. And so this is where it's actually a little bit different in that my wavelength for these others is going to be like twice my length, equal to my length, half my length, a third of my length, so on. And here it's like, oh, this is something weird. It extends not quite all of the way. So there is a mathematical way to do this, and basically you can look at your fundamental and realize that your fundamental is a quarter of the wavelength, that's what you see. So there is an equation for this. I think it's a little confusing to think through where it comes from, but hopefully you can at least understand why the fundamental looks this way, and if this is the shape of the fundamental, that this means the wavelength is actually 4 times the length of your tube because you only see a quarter of your cycle here. So if we zoom in on this, the modes that are allowed now, we actually still have different M values, which define the different allowed modes, but now instead of it being 2L on top, it's actually 4L on top. So this is a change from our open or our closed. The frequency now, again, you can just say that it's V divided by lambda, so you still have a similar thing in frequency. Again, the 4 is coming from the wavelength itself, but the most important thing to recognize is we don't have all of the integers of M. The only ones that are allowed are the odd ones. And the reason for that is if you had 2, for instance, if you said I had M equals 2, that would actually give you nodes on both sides. So that wouldn't be acceptable because you have to have a node on one side and an antinode on the other. So not only have we changed that 2 to a 4, but now only some of your M values, the odd ones, are allowed. So again, hopefully that can make some sense. This is kind of a confusing condition, but it means that your standing mode spectrum on these open-closed pipes actually do look quite a bit different than what your standing wave spectrum looks like on either a closed or an open.